我们今天这个讲的大概的这个整个的那个 outline 是这样，就是说我们大概有你能看得到的大概就有4个部分。然后呢，我只做一个开头的介绍，就是给大家讲一下，就是说我们今天的 linguistic structure 它是有什么样的分类，然后剩下的大部分，比如说从2开始，从2开始一直到4的话，是由我们剩下的2位就是同学来讲。所以中途我会换一下，就是那个 screen 会切出去，然后由他们2个来就是 take over。Excuse me。好，那我们就开始了哈。So today we are going to actually go to chapter 4. I guess it should be chapter 4, linguistic structure dependency parsing. So previously we have actually talked about a lot about the window classification, the skip gram model, or those kind of word embedding stuff. So previously we talked about, so the main topic is word embedding, right? But the thing is like our ultimate goal is to let the machine to learn the sentence or the paragraph to understand what that means. For example, I just gave the machine like one kind of sentence like, I really enjoy this drink. So the machine have to interpret that and try to understand the meaning behind those kind of bunch of words or combination of words or sentences or paragraphs. So that's the ultimate goal. So word embedding is just like a first step. That is how we actually going to represent those kind of words. So next we come to the second part, which is linguistic structure. So in order to understand a sentence or to understand a paragraph or file, usually the first step is we have to break the entire sentence into separate small parts and to understand the role that each part is going to play. For example, let's just start with the sentence say, I like drinks, right? So when you actually put this into the machine will saw all those kind of 3 words or one sentence right here. So that's a sentence. So the first kind of step, or basically the topic we're gonna get a little bit touch on is actually the parsing part. Like how do we actually parse out the specific components of the sentence right here? So from here, I would say, oh, for example, one way to do that is this is the subjective or subject. Sorry, that's a subject, and this is object, and that's a verb, right? So we basically parse in this way. I, subject, like, verb, drinks, object, right? So basically, that's kind of like the simple or the simplified version of the parsing or the topic of the parsing here. Okay, so what is parsing? So parsing trees, like usually we'll just build some kind of parsing trees, which I think like the 2 like lectures today will actually go into that part. In the natural language processing are actually used to analyze the synthetic structure of the sentences. Okay, so it's used to actually analyze synthetic structure. Basically, this is more like semantic meaning or semantic analysis. So we don't actually care about the frequency or the statistic part. We care about the meaning behind the sentence over there. So there are generally like 2 main types of use of the linguistic structure. Okay, there are basically 2 types. First type is constituency structure, or sometimes it's called phrase structure grammar, or sometimes it's called context-free grammars, okay, or it's called CFG here. So those 3 are just one type of structure. And this one, the second one, dependent structure, is what we are going to focus on today. So I'm going to give you a really simple introduction on that, but we are not going to actually go into the details of this. But what we focus today is actually the dependency structure. So start from the first one. So what is the constituency like a structure right here? What is the constituency structure? This is actually in Chinese it's called 选区分析. This is actually the most commonly used like a structure by human every day. So basically, we analyze the role of each kind of word in the sentences, and then we just give it a name, and then we link every single word together. For example, the goal is actually to analyze the words into constituents right here. Okay, or you can think about it is actually try to parse the words into several different kind of phrases. Okay, so you can think about that as phrases. Okay, so the core idea here is that the sentences are actually built out of the units that are progressively nested. Okay, progressively nested. So what I mean by that is, so for example, we can start with the words. That's the first, like, this is the simplest unit. Words is the simplest unit in the sentence, or any kind of like language over there, right? So suppose we have the word the cat cuddly by door. Okay, so that's the first kind of like a unit here. So next level is that we're gonna nest it into a phrase. So we're gonna combine that into phrase. So what can we do for the combine? That is, we can do, oh, the cuddly cat. That's one phrase. Second, by the door, another phrase. So this is a nominal phrase. That's a prepositional phrase. Okay, so NP here and PP here. Okay, here, PP here. Okay, and we can even do better. We can even do a bigger kind of phrase over here. That is, the cuddly cat by the door. We can link those two together, and this is a bigger phrase. Bigger phrase. So basically, we nest, can progressively nest each kind of unit into a phrase, into a bigger phrase, and into an entire sentence. But that's not everything. That's not the entire picture. What we care more about is the role that each single unit here plays. So let's dive into that part. Specifically, we start from the words. So those kind of words have, each kind of word have their own kind of role to play, or which is called part of a speech tag. Okay, so suppose we have the cat cuddly by door, and the here or the here is a determiners. This is one of the determiners we use every day, right? A, the, and right, those are determiners. So that's a determiner. Cat is a noun, right? Cuddly is adjective, right? And by is a prepositional, kind of like it's a prepositional noun right here, right? And door is another noun. So those are just their role to play, or their kind of part of a speech tag. That is what kind of role they play in part of the entire kind of like a sentence, or in this kind of phrase here. Okay, so next we're gonna combine them into phrases like what we did previously. But now we are gonna add a label on top of that. So we do the cuddly cat, like this one. So what is that? So basically, we actually use the determiner. On top of that, we add adg or adjective, right? And on top of that, we add a noun here. So together, this is constructed as nominal phrase, here, right? So again, we can do that as this one here. So by prepositional noun right here, the determiner, door, it's another kind of like a noun here. So it's a P and P, right? So together, this is a prepositional phrase, right? So we can also join these two together. That is the cuddly cat by the door. That is NP plus PP. So we actually construct a new NP plus, made of NP and PP. So in that way, we can actually, construct or create a parse tree. That is from here, NP, right? It has two parts, NP and a PP. And under NP here, we have, determiner. Oh, sorry, I should use another kind of here. So start with NP here. We do the backtrack. We do the backward kind of like, map here. It has two parts, NP, PP. And under NP here, we also have determiner, adg, and a noun. And for the PP here, we have P and another NP. The door is another NP. P is by, right? So this is by, this is the door. And we can even do a little bit further. We can decompose this NP as well to a determiner, which is Z right here, right? And door, which is a noun here. So yeah, so basically that's how the the parse tree is constructed. So we just give each kind of like the word a role to play as a part of the speech or their part of speech tag. Then we decompose a bigger phrase into small phrase into words so that we can actually create a parse tree here. So basically, yeah, that's how everything works. That's basically the same kind of graph I drew previously. Okay. All right, so that's just one of the structure. The second part of the structure is called dependency structure. So dependency structure, so here it's a little bit complicated. I'm just gonna give you guys one example. Then I will just leave the rest of the examples to Jiachen to actually explain a little bit more on this part. Okay, so first, what is dependency structure? So dependency structure basically shows which words depend or modify or are arguments of which the other words. So from now on, depend, modify, or arguments basically mean the same kind of thing. Basically, it's the same kind of thing. So what does depend on? What does depend mean here? Basically, is that one word is correlated to another word, or one word can be recognized as a child node in the binary tree from their parent node. Okay, so the binary asymmetric relation between the words or dependencies is usually depicted as arrows going from the head, which is we usually just call the parent, its governors or superior or region, to the dependency or the modifier, what we call the modifier or inferior or subordinate. Okay, so what does that mean? It sounds like really abstract. So let's just go through one example, try to think about what does the dependency relationship or structure actually mean. So first, we are going to start with this kind of example here. So all the dependency structure will always have one, the aggregate head or the top kind of like node here, which is root. Okay. All the dependent structures start with a root. That's a rule, which I think Jiachen will mention later. Okay. So I'll select the first word here as a root. Okay, and the example here I'm looking at is looking in a large crate in the kitchen by the door. So look is a root. Okay, so that's the first step. Second is we need to find a word that is correlated to look, or that is the dependent of look. And turns out it should be crate. It should be crate. Okay, so dependent structure always start from the root, then goes to verb, or I don't even understand like how English see that. It's called this 谓语. Okay, you all start from root and then go to the verb here. Okay, so that's the first step. That's the second step. Okay, so create is a dependency of look, or you can say create modifies look, or create is a modifier of look. So it's all the same. But most of the time, I'm just gonna say, create is a dependent of look. Okay, so that's the first step. Now, if you look at the create here, then we can go from there again. What is the modifying create? Or what is the dependency or dependent of create here? The dependent of create can be large, right? Large create. So large is like, derivative from create. So it's a dependent right here. The second dependent is the crate, the large crate, right? So the is also part of the derivative of the crate. And in the crate, so in is also a third dependent of crate. Okay, so that's the second part. We can also do a little bit more, right? So crate is actually just like a one of this the second step we actually went through. So we can do a little bit more to another direction. So what about another kind of dependent of crate? So another dependent of crate could be in the kitchen, right? This phrase is another dependent of crate, in the kitchen, right? And in the kitchen, we can decompose a little bit more. That is, the kitchen can be recognized as a new root, and the and the are both the dependent of the kitchen as well, right? dependent location as well. And we can also do another kind of direction. What's another dependent of the crate? Because crate is by the door. So this could be another dependent of the crate. So now we are landed at this root here, by the door, those kind of phrase. So what is the dependent of the door? The and by. Okay, the and by. So that's basically how we actually create a dependent structure here. So that's basically, that's a little bit complicated example here. So I'm gonna do one more, just one more really simple example. Then I'm actually gonna, finish this part here. Okay, so let's look at this example here. Senjo's cops kill man with knife. Okay, so this is the example we're actually going to go through here. Senjo's cops actually kill man with a knife. So there could be two different meanings of this kind of sentence right here. So okay, yeah, I'll upload the notes somewhere later after I finish the lecture here. There are two different meanings of this kind of sentence where Sanjo's cops kill man with a knife. What are the two different meanings you could actually come up with? Think about the first one. What's the first kind of meaning you can come up with the sentence right here? Sanjo's cops kill man with knife. Any thought right here? You can open your mic and talk loudly in the meeting, in the Zoom meeting we are actually having right now. Sanjo's cops.
Somebody kills a man using knife.
Somebody kills a man using a knife. Yes, exactly. That's the first kind of like a meaning, right? So the police actually use a knife to kill the man, right? That's our first kind of meaning. Okay, let's do that first. So suppose this is the first meaning. So we are going to start from the root. And this is the fake root here because we don't have any root right here yet because we don't actually.
Can I jump in to ask a question? So,
sure, yeah.
So how do you usually choose a root? Do you choose root randomly, or do you like specifically choose one word at the start, or do you usually just randomly choose a root and start from it?
No, you don't actually choose a root randomly. So it depends on the structure of the sentence right here. If you have like a sentence like this, if you have the sentence like this, you're probably gonna choose the first word. Look here, which is a verb as a root right here. But for this kind of sentence right here, the verb is already in the middle, which is kill, right? You can actually, that's actually what I'm going to go through next. You can actually start from here and go to that direction, this direction. So that cannot be the root right here. So the root has to be unidirection. So it has to be start from the root. You can also go to another direction. You cannot go back, right?
So you're saying that usually we should choose verb or starting point.
Sometimes I haven't finished my sentence yet. Sometimes we don't choose a word. We just choose a fake like a root as like a starting point.
Okay.
Yeah. So it depends on the structure. So the root is actually, there's no kind of uniform rule like which kind of word you should choose as a root right here. Sometimes we do have a root. Sometimes we have to make up a root. But it all depends on the structure. So for first kind of question, do you understand what I talked about right here?
Yeah.
For this one. Okay, now let's go to this one here. Let's see the difference and see why we actually pick a different root right here. So for this one, just take my words right here. I just take a fake root. Okay, so there's no word here. I just create a root myself. Okay, so after I create a root myself, suppose the root is here. So I'm actually just gonna write it here, root. So the next word that's actually going to correlate it with root is actually this word, kill. Remember, root always follows by a verb here. So it should be kill. So if kill is like the first sentence or first kind of a note here. So root here, it goes to kill. So if you just build a tree here, it goes to kill, right? So like this is the first meaning. So starting from here, we can do a little bit more, decomposition. Sanjo's cops is actually the subject. Sanjo's cops is subject. So we can do a little bit more here. So cops, subject. And man here is an object, right? We can do that. So now Sanjo's cops and a man are both dependent of kill here, are both dependent of kill here. Okay. So since the police are going to use a knife to kill the man, so another kind of dependent of kill could be the knife, right? Because cops use a knife to kill the man. So this is a derivative of the kill as well. It's linked to kill. So this is another objective, another kind of dependent of knife. This is called a modifier of nominal. You don't have to understand, you don't have to remember this. You just need to remember, those two words that kind of related right here. Okay. So start from here. So we are now at knife. So I can just do a little more tree here. Knife. That's NMOD, right? Next, I'm actually going to start from the knife here and jump back to the width. Jump back to the width. So now width is actually a dependency of a knife right here, right? So now you understand why actually we made up fake root right here, because the verb is actually not at the beginning. The verb should go this direction and that direction, right? If you make this kind of root right here, of course you can make a kill as a root right here. But the things like in sentences right here, what if you have like two verb over there? You have two verbs and you have two note, but we only need one root over there. So we better just make a single root here so that we can just link it to one verb and another verb right here. Okay, but here you only have kind of like a one verb right here. Look, so you can make that as a root for sure. And actually for this sentence, you can make a kill as a root for sure. You can even make that as a root as well. So that's just like this example. But what if you just have a kill man with knife and save a man with children? Then you have to make a fake root yourself because you have two verbs right here, right? Does that make sense?
Yeah.
Yeah. Okay, that makes sense, right? So that's how we actually construct this one here. So basically, yes, if you only have one word in the sentence, you can use that as root, or you can just construct a root. But most of the time, we just construct a fake root at the top. This is more like conservative strategy because we don't know how many verbs we are going to use next, the root after the root over there. So we better just construct a fake root on the top so we can link it to multiple kind of verb over there. This one and this example, sure, you can use a kill or look for as a root right here. But for more complicated kind of structure, you better just create your own kind of root on the top. Okay, so that's our first meaning. The second meaning is, Sanjo's cops actually kill man with a knife. That is, the man has a knife. So the cop killed the man and the man has a knife. If that's the case here, if that's this kind of case here, then we're going to have, again, we're going to start from the root here, right? And the root is going to be linked to kill, or I should do it the other way. Yes, yeah. Root is actually, kill is actually a dependency of the root right here, right? So after that, we can do a little bit more. Again, this is the same. So Sanjo's cops is a subjective with the kill, and man is the objective with the kill. But now, with knife, this kind of phrase is used to describe man, not kill. So with knife now has become the new kind of like dependent of the man here. Okay, so here with knife is a dependent of the man, not kill anymore. So here is kill. Okay, so the next part is actually the same. So with is the dependent of the knife right here. Okay, so this is called ambiguity. For this one, this is called propositional ambiguity because the ambiguity tags or those kind of meanings of a word where the diverge like opinion or different kind of opinion gonna occur is actually on this part, on the propositional phrase. Okay, so it depends on the source. So if it's nominal phrase, then it's called nominal phrase attachment or a nominal phrase attachment ambiguity. But this one is the propositional phrase. So this is called a propositional phrase, propositional attachment ambiguity right here. Okay. So basically, that's how we actually construct the structure, the dependency structure of the different between different words or phrases or into within a sentence right here. Okay. So I think like Jiachen will give you guys more, a little bit definitely more details on this part. So I'm actually gonna, yeah, I'm actually just gonna stop right here and shift it over to Jiachen. But before that, any questions so far?
Like just wondering if the title is really like this, so how would the machines identify the real idea of the writer? So
that's exactly what Jiangjun is going to talk about later in this lecture. So don't worry, we're not there yet. We're going to go step by step. We're going to, actually start with the structure first. Then we're going to talk about the models that can identify different structure or parse different kind of like a word, different kind of parts of the sentence into different kind of like phrases and recognize the meaning.
cool. Thanks, Daniel.
Yeah. All right. Any other question? Yeah, Jiangjun just said we'll actually talk about the machine later. It's called a state machine, which is, it's very funny, actually. I found it very interesting. Any other question right here? Okay, so as you can see, I just want to make a summary here. The difference between the first structure and second structure is the first kind of structure is context-free. It's context-free. I don't really care about what context you were talking about. I only care about the individually isolated role that each phrase is actually, each phrase is placed over there. I don't really care about which word you are depending on or what kind of phrase you're next to, right? But the second one is like, I'm gonna create a correlation between different phrases, different word, so that I can find, correlation tree on top of that to actually construct the correlation or the meaningful kind of correlation between the different words over there. So those are two different totally different kind of structures. But today we're not going to go through the first one. We are actually going to focus on the second one. So that's called dependency structure. So now I'm going to head over to Jiachen for the dependency structure. More details coming up. Okay. All right, I'm going to stop sharing. Stop. Okay. Your turn.
Okay. Okay, looks like I'm sharing my screen now. Yep. Okay, thank you, Daniel, for making my work super easy. So basically, you guys have already heard, what he talked about is basically what I'm going to talk about. I'm just going to repeat what he was saying. Hopefully this clarifies, the questions that that people might have. Yeah, so I just want to start with like the goal of this whole thing. Like Daniel said, we wanted to make sure we understand how human language works. That's kind of the point of doing any work with NLP. From the previous chapters, we already looked at the the word embedding part, word to vec, word the skipgrams and everything. We look at a window and we look at what neighbors a word keep, and we're trying to figure out the meaning of that word based on the neighbors that the meaning of those neighbors. And from my understanding, what we're trying to do right now, which the dependency structure that we're trying to explain right now, this thing is trying to look at what kind of relationship, what kind of dynamic is in that neighborhood. So we know, we can say something like, look at the cat in the kitchen. Cat is next to the or kitchen, but what is that? What are the relationships between those words? So that's like the whole point of having the concept of dependency structure. Like Daniel said, we kind of separate the words into the first would be the roots, and then we try to find what are the dependents for each word, or who is the master, or the whose dependent it is that each word are in the sentence. So this is just an example of how we're going to look at this. And like Daniel said, usually we look at a verb. We start with a verb, and that will be the root, or that will be our starting point to figure out the dependency structure. In this particular sentence, we start with the word look. So what are the words that makes the word look have meaning? So if you just say look, it doesn't really mean anything. You gotta look at something first. So we're looking at the cat. So the cat is a dependent of the word look. There's not really any other words that are have the similar relationship with the word look, because kitchen, we're not looking at the kitchen, we're also not looking at the door. The kitchen and the door, these two words, or in the kitchen and by the door, these two phrases are actually describing something about the cat. So that's how we know, these are the dependents of cat. And now we're left with, all these smaller words like at, the, or in. So these have their own like smaller structure. This is how I think of a sentence, breaking down a sentence when we're thinking, when we're trying to figure out who is the dependent of whom. So the reason why we would want to figure this out is that you guys can think of a lot of grammatically correct sentences that can cause confusion. One of the example would be the San Jose police killed someone sentence that Daniel was just talking about. We have a lot of examples like that. Some of them are quite funny. I would say we can look at these two examples, which these are essentially the same sentence. Scientists count whales from space. So there are two ways of understanding this. The first will be we start from the word count, because that's the main verb in this sentence. And so what are we counting here? It is the whales that we're counting here. And who are doing the counting is the scientists. And where are we doing the counting from? Is from space. So you can kind of, form this kind of relation. You have these three arrows. So scientists, whales, and from space are all dependents of the word count. And we have this mini structure from space. So this is one way to understand this sentence. And there's another way of, there's a more psychedelic way of understanding the sentence as well, which is scientists are doing the counting, and they are counting whales, but those whales are actually from space. So that's a different way of understanding this. And the main difference is this blue arrow. In the previous one, this from space is a dependent of count. But in this example, you can also say that the space from space is a dependent of whales. And same minute structure here. So like, this sentence is grammatically correct, and they are the same sentence, but there are two ways of understanding understanding the same thing. And I would say that normally the first one would be the correct interpretation, because unless you're trying to write a psychedelic story or something like, or space related story. But in most cases, I would say that the first one is the correct way of understanding. So this is also, why we need these arrows, why we need to figure out what is dependent on what. So we can avoid this kind of ambiguity with that exists in the English language. Okay. Oops. Okay, there are some, okay. So, okay, I'm just gonna pause here for a little bit. And do you guys have any extra questions? Hopefully, it helps you to understand what these arrows mean, and, why they exist in this way. Okay, well, I'm just gonna go forward then. So we have this whales example, and I think Daniel also mentioned at the beginning that the outcome that we're expecting from the from all these parsing process is that we wanted to essentially transform a sentence into a tree structure. So, here is a incredibly boring sentence, and we wanted to make this into a tree structure. And how are we going to make that? So it actually, the tree structure represents all of the arrows that we were adding to these all the arrows that we put in. So let's start from putting in arrows for this sentence. So bills on ports and immigrations were submitted by Senator Brownback, Republican of Kansas. So if we're looking at the first sentence, so we can probably tell that the verb that we're looking for here is submitted. So this person did something. So that's how we know that something was submitted by someone. The bill was submitted by this person. So we can tell this is how that's how we figure out what are the dependents of submitted, the bills and this guy. And also, like, we know that the bill is on ports and immigrations. So these two things are telling us more about the bills. So ports should be a dependent of bills. And I guess there's kind of a flat structure, because it's and something. So you can say that immigrations is a dependent of ports, and wouldn't make sense without the word ports. So it's also a dependent of the word ports. And what else are we missing here? So also, Republican of Kansas is providing more information about this person. So this part should be a dependent of this person. Okay. Also, it's a senator. So Senator Brownback, and Republican of Kansas is talking about the same guy. And here's the mini structure. The Kansas is giving us more information about Republican or this person's status. And when we take all these arrows and make them and these words and put them into a tree structure, it basically will look at this. So we start with the root, which is submitted here. Here's this arrow to bills, and we have bills here, and we have work here, and also who submitted something is this Brownback guy. So we can put every sentence and every structure that we came up with using these arrows into the tree structure. So apparently some scientists figure out that it looks like we can do this to a lot of sentences, and these structures are representative in the English language and also in other languages too. So you can sort of figure out similar structures for different languages. So they think okay, we should keep a copy of all these structures that we came up with, and so people can reuse them sometimes, and people can also go for reference, look at these sentences as a reference when they don't know, when the ambiguities comes up. So when we have the whales example, we should save the first example as the correct answer on how to understand this sentence. So other people, next time when people encounter this kind of sentence, they can just go refer to whatever that's stored there, so they know that it's not really a psychedelic story. So that's how some people came up with this tool, or this it's like a database. It's called Treebanks. What this is basically a bunch of sentences with its structures figured out and stored in this website. So if any of you are interested, you can go and look. It covers a bunch of different languages. It has English, Chinese, Finnish, all kinds of languages, and a bunch of examples there too. I think we're going to talk about this later, but everything that's stored here can be used, can essentially be used as training data when you're trying to, what we would actually feed, when we were trying to teach the machine how to figure out these arrows and the tree structure. You know, I remember that there is an earlier question on how to figure out what the root is for a sentence. Up until this point, every sentence that we look at, we basically are using the verb as the root. You know, from this sentence, you can see that it's actually, there are other options. So this sentence is like, George Harrison said in a video that something something. So, you know, this, for the first part, we're using said as essentially a root, because, you know, that's is similar to the structure that we have been looking at so far. But in his quote, here is another sentence instead, inside this big sentence, which is Oasis is a very untalented band. And here is pretty, I think it's pretty obvious that if you only look at this portion, the root word inside this, you know, this sentence within sentence is actually band, because there's a bunch of arrows coming out. All of these are, you know, these other words are like, they shouldn't be playing or whatever. These are all describing the word band. So, you know, I guess I'm just echoing what Daniel said before. It's what the root is depends on the structure of a sentence. You know, I would say that, you know, if we don't have Treebanks, it will take us a long time to figure out what the correct structure is for every sentence that we're trying to use, or we're trying to train the machine on. But it's good that we have Treebanks. A lot of people have already done the work for us, so we can use this directly. Yeah, I also wanted to show you a little bit of, you know, the Chinese portion of the Treebank. Can you still see my screen? Yep. Wait, why is there a block underneath? Okay, but you know, this is like, so this is the Chinese portion of the Treebank, and you can see that they are breaking down a lot of sentences, and they're adding this POS tag to different words in a sentence. I think this is, you know, this could be very interesting, and if anyone is interested, just go to that universal dependencies, go to this website, and you will be able to see more examples on different languages.
Sorry to interrupt you a little bit, like Jiacheng, because there's like a black kind of like a box at the bottom.
Yeah, I noticed that too.
Yeah.
I don't know what that is.
I guess like, can you actually, you know, exist from this like a screen share and reshare the screen again?
Okay.
Let's try that. See whether that works or not.
1 second. How do I stop sharing? Oh, here. Okay.
On the top, there's yeah. Now you like share it again and see how that works. Okay. All right. Okay.
Do we still have it? Is it still there?
Yeah, it's still at the bottom. But yeah, I think you probably. Yeah, but now it's much
just
better,
at the
right?
bottom.
Yeah,
I don't know why it's there. It's just weird.
Yeah, just go ahead. Yeah, no,
okay.
it doesn't matter.
I hope it's not. Yeah, I hope it's not blocking anything. So, I do want to pause here for a little bit and see if you guys have any questions. You know, this example is too complex. We're not gonna look at that. Let's just go back to this example, or, you know, any of the Wales examples. So yeah, I guess just want to make sure that everyone's clear on how we analyze a sentence and add these arrows.
I do have a question which I actually want to spark more discussion on this probably. Like, when do we actually stop like parsing the sentences over there? Like, what is the ending point of the you know, those kind of long journey or the parsing the sentence right here?
Yeah, I think one of the goals here is to try to find a home for every word. Or, you know, so each word, it gotta be either you are the root, so you are not a dependent of anyone, or you are a dependent of some word in a sentence. So I think, you know, we gotta figure out the situation for each word. So essentially we need to look at each word and either assign them to some other words, or, you know, make the judgment that they are the root, or that is a root, because there should only be one root. So in the, yeah.
Is the dependency tree, is there only one correct dependency structure, or it could be like multiple?
Yeah, I think the point is to have, one correct way of, one correct structure. Because, like in the whales example, it's pretty clear that, these two are essentially two different structures. And we will say that the first one is the correct one, because the second one doesn't make sense. So
yeah,
I think the standard to judge on that part is like, the question is like, we could have many different kind of trees for sure. There's no kind of unique like the tree structure over there. Like for, like Jiachen just said here, for the whales, like the example here, we could have two trees here. So, but we could have two trees and then we have two kind of structures. But how do we evaluate which one is better? That's why we're actually going to use the tree banks. So tree banks is like, it collects as many as commonly used and widely spread, kind of like trees over there, and we try to compare whether we have those kind of structure in the tree. If we like, and then we actually just give it a score, which I think like Jiangjing or any one of you probably gonna mention later, like how we do those kind of evaluation on the tree structure. We are gonna give it a score for both kind of trees and see which one actually get a high score. Then we just use that tree as a final kind of like decision or the judgment we actually have on that sentence over there.
I see. So if a sentence have, say, multiple verbs, you can start with any verb as the root node, and then you can construct like several trees. And then based on this like tree bank algorithm, you evaluate different like say trees and see which one has the highest score, and then you pick that one as your dependency structure. Is that like a correct understanding?
Exactly. Like you could have like an infinite number of trees over there for sure. Like it depends on how long the sentence is, how many verbs you have, which verb you pick it up as a first kind of like a node over there. But later on, I think like Jiachen or Jingjing is gonna actually tell you guys there are some kind of certain rules we have to obey when we actually construct a dependency tree. Like one is that we only have one root. Second, it should be like a one direction. It cannot be like a kind of a recursive circle. It cannot be like closer circle. So that is, you can only go from one word as a head to its children. You cannot go back. So if you pick the wrong word, probably you can go back. You loop through like you actually have to close the loop. If that's the case, that means your tree is definitely not the right one, right? So basically, there are different kind of structure for sure. Infinite number of structure depends on which number you pick as a root. But most of the time, we're just really careful. We want to pick like the right starting point so that we don't actually have to close like a tree later.
Okay, cool. Thanks.
Yeah.
yeah, I also saw a question about the dependencies for immigration, ports and immigration. Someone said that immigration should be a dependent of bills as opposed to ports. I feel like I actually have the same sort of questions, and
that's actually another kind of structure, right, Jiachen? That's another structure. Of course, you can think of this kind of like a sensing that way. That's going to be a different structure. But here, the example, like Jiachen said, it's not about the right one. It's about one way to construct the tree. It could be another way to construct the tree as well. Yeah.
Yeah, well, the way I understand this is that, I think they probably first assign ports and immigrations as, that whole thing as a whole as, a dependent of bills. And they're further breaking down the structure inside ports and immigration. It's sort of like Republican of Kansas. From my understanding, I feel like that whole thing should be a dependent of Brownback. But within itself, it has its own structure. So that, so Kansas is the dependent of Republican. That's how I understand why, you know, immigration is not a direct dependent of bills. I believe that if you shift the position of immigrations and ports, the answer will be different.
Yeah,
That's how I understand this. Okay, so yeah, so we have this, we have our tree, and you know, someone processed a bunch of these trees and they saved into Treebanks, so we can use this for other purposes. So I just wanted to, you know, kind of just sum up what we've gone through so far. So there are a few principles, like Daniel said, that we want to obey when we're trying to figure out the dependency structure of sentences. So for example, we want to find, the goal is to find words for which each word is a dependent of. So you want to find home for each word. Or you want to, you know, if someone doesn't have a home or doesn't have other words to depend on, then it's the root. And a sentence can obviously get very complex, and sometimes you can't find one single root. And when that happens, you manually assign root, just like the word ROT, as the root of the whole sentence. The reason why we want to have this manually assigned root is because that we want to make sure that the final outcome is a tree structure. If you want a tree structure, so like this part, if you wanted to look at this, you gotta have one head. Like there can't be two different heads on top. So when you find, you know, when you see there's trouble figuring out what the root is, just assign a root word and link everything to that. So you know, this is an example of, you know, when I assign a root word manually. If you're just looking at the sentence, it's pretty obvious that you got to start from give, and who. Okay, yeah, give is dependent of the word root. But if you're analyzing this, you know that, you know, give what? I give a talk, and when do I give that talk? Is tomorrow. Who's giving the talk? Is I. So these are the arrows that we. Oops. Yeah. Yeah, and so the talk is on bootstrapping, and it's like this on bootstrapping little structure in here, so we have this arrow. I don't know if you guys have noticed, but like all of the previous sentences that we have looked at, all these arrows, they're not crossing each other. By crossing, I mean what happens here with this red arrow. So bootstrapping is a dependent of talk, and tomorrow is a dependent of give. So these two, like this one between give and tomorrow, and this one from talk to bootstrapping, these two are crossing. And the reason why they're crossing is because we put this on bootstrapping, which is describing the talk, at the very end of the sentence. This crossing wouldn't have happened if this sentence is just like rephrased to, I will give a talk on bootstrapping tomorrow. If that's the case, then this last part will be moved to the front, and this crossing wouldn't have happened. This is something that, you know, we, I feel like this is probably something that the machine is having a little trouble understanding. So like for most of the cases, and including the example that I show here, which is a large sentence, and looks like everything is not, like nothing is crossing here. They're all either inside each other, they're just like flying over each other, but they don't have, you know, what we have here, like this red arrow. So this is something that the machine is having trouble processing. And I think for now, we're just going to treat this as a special case. We still allowed it to exist, but I guess at least for this lecture, we're not going to consider situations like this. So all the sentences that we're going to try to parse is going to look like more like whatever that we see here. So they will not be crossing. And also, that, as Daniel mentioned before, we can't have any cycles, which means, you know, let's say I have tomorrow give goes to tomorrow and tomorrow goes to talk or something like that. If this kind of cycle happens, then it would not be possible for us to come up with a tree structure for a sentence. And remember the goal, like we have to come up with the final outcome needs to be a tree structure. So I guess that's probably, the rules or the things that we need to consider when we're trying to parse a sentence. We got to have a single root, and if there's no single root, just manually add a head to it, and there shouldn't be any cycles, and ideally there shouldn't be any crossings, but it happens. It's a natural part of the language, and we allow crossings to happen, but we're not going to parse sentences with that kind of crossing, which is called non-projective sentences. So I think that's it from my part. I think the next part would be how the machine view all the parsings and the structures, and how are we going to tell the machine how to go through each words and figure out these arrows. I guess I'm just going to pause here and see if anyone has any questions. Okay, sounds good. I'm going to shift this to, okay, so Jiangjing, do you want to take over? Oh, is there questions in here? Let me see.
Okay, let me share my screen here. Can everyone see my screen share? Hello?
Yep.
Okay, great. Okay, so now I'm gonna talk about the method of dependency parsing called transition-based parsing. It's also called deterministic dependency parsing. So it has been enormously influential in practical deployments of parsing. So when Google parses web pages, I'm not presenting this slide. Okay, so when Google parses those web pages, what they use is transition-based parsing. And this method is mainly popularized by Nevers in 2003. So there are two very important concepts in a transition-based parser. One is called configuration, and it's also called states, and the other is called actions or transitions. In a configuration, there are three things: a stack, a buffer, and a set of dependency arcs. So the stack is a pile of words that I built to deal with. And the buffer contains all the words in a sentence that I haven't dealt with yet. And in this transition-based parser, we move the words from the buffer, which is like a backstage, to the stack, which is the front stage, and then generate some dependency relations. I'll give an example on this in the following slides. Okay, so a configuration or state can be written as like C, which is a triple of stack, buffer, and dependency arcs. So if we write a sentence as S equals this thing, it means it has N words, and it starts with W0 to WN. But W0 is not the word in the sentence, it's a root we create at the start of the sentence. Okay, if you see this, like A equals triples, don't worry. It means the WIR1WJ means that the word J is somehow dependent of word I, and the R is their dependency arcs, or you can call it a relation. Okay, so what's in the initial configuration? Can you think of that? When we start parsing, what's in the configuration? Configuration is stack, buffer, and dependency arcs, right? In the beginning, we don't have anything in the dependency arcs, so the set of dependency arcs will be an empty set. And the stack has only the root in it. We also always put the root in the stack at the beginning. And the buffer has all the words of the sentence. And at the end of the parsing, we have nothing left in the buffer because we have parsed everything by the time. And we'll have nothing but the root left in the stack because we will move the words, other words out of the stack. I'll talk about those actions in the next slide. And we will have a set of dependency arcs. So these are what the initial state and the final state will look like when we parse. Now, this slide shows the 3 actions we can choose from, which is shift, left arc, and right arc. The shift is very easy to understand. It's just the action of moving a word from the buffer to the stack. So remember, the stack is the pile of words we are dealing with currently, and the buffer is a pile of words we haven't dealt with yet. So this action, shift, is like pulling a word from the backstage to the front stage. And here are 2 actions called left arc and right arc. They're like twins going to opposite directions. They both have 2 steps. So the first step of the left arc is adding a dependency arc to the set A, which is a set of dependency arcs. And the WI, the notation here means the top word from the stack. And the WJ here means the second top word from the stack. So this combination means the second word is dependent of the second top word is dependent of the first top word, right? Remember the notation we just talked about in the slide. So this is the first step. The second step is to move out the WJ, which is the second top word from the stack. And as a result, we leave the top word in the stack. So how to understand this action intuitively? My summary is this action adds a dependency arc, then it removes the not so important word out of the stack and leave the important word, the core word or the head, governor, superior word in the stack. This is just my summary, so please don't quote me on this. So when we do with the left arc, we sort of make a decision that the top word, WI, in the stack is the important one. And the second top word, which is the dependent of the top word, is not. So we remove the second top word out of the stack. After understanding the left arc, the right arc will sound quite familiar to you. So the first step of the right arc action, again, is to add a triple showing the dependency relation to the set of the dependency arcs. So again, in this triple, WI means the top word from the stack. And the dependent, it is the dependent of WJ, which is the second top word in the stack. So now what is the next step? Just like left arc, you might have guessed it already. It's moving out the top word WI from the stack, because here WI, the top word in the stack, is a dependent. We don't want the dependent word remain in the stack. We want to keep the head word, the governor, the superior word. So that we keep the second top word, WJ. I'll have an example to show you the actions. The example is a simple sentence, I ate fish. So it has 3 words, but we always put the root as the start of the sentence for this parser. So in the beginning, we only have root in the stack. Can I do any arc? No, I can't do any arcs because there's only one word, which is a root in the stack. So the only action I can do is shift. So I shift, sorry, I shift I from the buffer to the stack. And now we have the stack, which is root and I. I is the top word, root is the second top word. I can do an arc right now here to analyze the dependence of I to the root, but that would be wrong because we know that the sentence is I ate fish, right? So the right thing to do seems to be adding another word from the buffer to the stack, which is the ate. So now the stack has I and ate. So I can do an analysis now as an arc here. We can tell that I is the subjective noun to ate. So we can say the second top word, which is I, the dependent, is not so important. So we can add the dependency arc to the set A, and after doing this, this slide. So we can do a left arc here from root I8. Because the second top word I is the dependent, and we would like to remove the second top word and leave the top word on the stack. Does it make sense? So after doing this action, we have 8 and root here in the stack because we removed the second top word, the I. And looking at the stack, what shall we do right now? I can do another shift to move the fish from the buffer to the stack. Since the fish is the objective noun of 8, it is a dependent. Okay, so after shifting, it's like this. Fish is the dependent. So we would like to remove the fish from the stack. So we do an right arc here and throw away the useless word fish. And now the stack has only root and 8. And the relation, or the dependency arc we add to the set of dependency arcs is fish is an objective noun of 8, and 8 is the governor, fish is the dependent. So after we do this, the buffer is empty. And looking at the empty buffer, we know that we are close to the end of our parsing, right? So how do I deal with this stack, 8 and root? So root is like growing in the stack. It can't be removed. It's a rule here. So we want to remove the 8 word from the stack. So what is the action? It's right arc, right? By doing a right arc, we can remove the top word 8 off the stack. And in this action, our analysis is 8 is a dependent of the root, and the relation is the root. Root is like everything's governor, core. What's the other word? Superior. So I drew a table on the top left to record our parser. It's clear that the stack in the initial state and the final state, like stack buffer, they are consistent with what we talked about in a normalized way. So I mean to ask a question here, which is, what are the conditions of doing a left arc and right arc? Remember, these two actions are like getting a dependency arc and move a word out, right? So by looking at these two actions, you might have realized already that the common condition for both left arc and right arc is it must have 2 words. at least 2 words, right? Because we will remove either the top one or the second top word or second top word. So there must be at least 2 words here. And there's a specific condition, excuse me, a specific condition for left arc, which is the top word cannot be root, because by doing a left arc, we remove the top word, and the root can never be removed from the stack. It's a rule here. So the special condition for left arc is the top word cannot be root. I can't think of any example here that's like top word is root, but that's what the official notes says. So I added here. So by using these actions, we're left to explain how we choose the next action, right? I chose the right one because I knew the meaning of the sentence. It sounds like me learning, not machine learning. So how do we apply machine learning? Can we give a machine some inputs like the words and their dependency arcs, then use some evaluations to make it produce an output like a sequence of actions as a prediction? So Neveu and Hall provides a very fast linear parser in 2005. It was an enormous breakthrough. It's also widely used until 2014. So I'll refer this parser, which is called mult parser. I will refer it as a conventional parser when we talk about in the next slides.
Sorry,
Yes.
just to make a little bit of compliment on the mult parser.
Sure.
So yeah, just like Jing just mentioned, we use machine learning to actually do this, but how do we actually embed machine learning into this parser is that, so if you look at left table, we got a bunch of actions. So our kind of decision is to understand what kind of next action, what kind of decision should we make at each step. So machine learning step into this kind of entire parser, playing a role of making decisions for us. So basically we have 3 actions: shift, left arc, and right arc. So basically you put all the stack and buffer and previous action into the machine learning. For each step of there, the machine learning gonna do a classification algorithm and tells you which step to take. What's the possibility of taking shift? What's the possibility of taking left or right arc? So that's the core idea of how, you know, the mult parser actually is going to use the machine learning for the classification, and on top of that to make a decision on the actions. So yeah, that's everything. Yeah.
Yes, that's exactly it. So it's like I'm in a particular position in the parse, and I'm gonna build a machine learning parser or machine learning classifier, and that machine learning classifier tries maybe every action, and it has some evaluations like accuracy scores, and as a return, it will tell me what to do next step, like what's the best next step. So these 2 brilliant people, Chen and Manning, built a neural dependency parser. They compared their model, this one, they highlighted in pink. They compared their models with a conventional one. A mult parser is the Neveu parser proposed in 2005. They used 2 accuracy scores, UAS and LAS, and their speed to evaluate the models. So mult parser, people love it. It's very good. It has a high accuracy score, UAS, unlabeled attachment score, and it's very fast. It can parse for 69 English sentences per second. There are other people proposing their more complex parsers. They're a bit more accurate than the mult parser, but the cost is they parse much slower. And the new model, which is proposed by Chen and Manning, it's called neural dependency parser, it's almost as accurate as the most accurate conventional parser, and it's incredibly faster. It can parse 654 sentences per second. So our next section is to talk about the neural dependency parser. So this is like overall picture, overview of the parser. This parser has 3 layers, just like an ordinary plain neural network model. The input layer has features extracted from the current configuration. I'll talk about them in the next slide. The next slide, exactly. So the hidden layer has neurons making weighted combinations of the inputs, plus a bias, okay, plus a bias here. Here they use a cubic function as the activation function. Well, they, how to say that, I don't know why they use this function, but like what they mentioned in the paper is this function is better because they believe that this function better captures an interaction between the 3 elements, because when you expand this function into a long version, you can see the interaction, which is they time each other. And after they apply this activation cubic function, they compare this function to 3 other functions called time, sigmoid, and identity function, and then validated the success of their choice. So they did not prove that this cubic function is the best activation function in the world. They just validate that this function performs better than its competitors, which are the other 3 activation functions. So their logic is like, it makes me think about a classical story or theory. That is, if you and your friend were chased by a bear, you don't have to be the fastest person in the world. You only need to run faster than your friend. So this one is like the same logic. It's their choice of this activation function is not proved to be the best function among all other possibilities. It's just better than its competitors. For the softmax layer, I haven't am I in the, okay. I think the hidden layer is like, do you have any question about the hidden layer or anything about this parser? Okay, so above this layer, there's a softmax layer. They use a softmax function to get the output, and they use a cross entropy loss function. And the aim of this parser is to predict a transition sequence from some initial configuration C's to a terminal configuration in which the dependence parse tree is encoded. So do you remember we have like a set of actions, right? A softmax function is like a logistic function extended to multi-dimensional space. So what the softmax function does here is to tell me the probabilities of choosing the 3 actions. So this is an overall view of the neural. Oh, I saw like chats here. Sorry, I did not see the chats before. Let me look.
Le Yuan just asked a question like, how many classes?
How many classes? Like classes of what? Sorry, I'm a little bit.
In the softmax, like how many targeting classes are we trying to classify into? Like 3, like the 3 actions. I saw like more than 4 nodes, so I'm a little bit curious.
Like for now, the simplest one is 3, but of course, like you could have more than 3 actually, because we only do left arc, right arc, like shift. But this is actually dynamic programming, right? So you actually kind of like use dynamic and structure like a window to actually slide to the right or to the left to add on top or to shift to get rid of it. So there could be other kind of actions which are more complicated. So that's why, generally speaking, we could have more than 3. So that's why you have like, 4 or even like more different actions over there.
Sorry, so they can have more actions than like shift, left arc, and right arc.
Yeah, basically, yes.
Okay. Can you give an example? Like say you say like get rid of, like what does that mean? Like I don't put this word in the dependency tree.
So if you look back to the I eat fish, that one, you actually, so can you go back to page 15?
No problem. 15. Like
Yeah.
this one.
So if you look at the first line here, after we construct like the relationship between 8 and I should just get rid of I. So I has been
but I thought
eliminated.
that's left arc.
That's left arc, yes. But what if like, think about the way that, how should I explain this? So think about when you have like more complicated structure, like not just like 2 words right here. Let's think about, I accidentally add fish, right? If you do that way, then you have to like a nasty, like, kind of like a left arc inside that. So you have the nest and left arc inside that as well, right? So in that way, you have like a little bit more complicated action, which is the left arc on top of left arc.
Okay, say if we have like say more than 3 actions, don't we need to know how many we have like to select from so we can construct
so
this
basically
neural
you have to construct, so neural network is only for decision making on which actions you should take. It's not for the entire model. So this is just that like part of the model. So you
I understand, but like say the total like number of actions that I can choose from.
That's what
like,
you
is
already
there a
have
number
at the
or
beginning,
we
right?
it's do we have like say do we know like a number for that or we don't?
Oh, for the transition-based parser, it depends. Like the traditional one only has 3, but for some other kind of new invented, like still like transition-based parser, it could be 4 or 5. So it depends like how you modify the model. Yeah.
Okay. All right. Cool. Thanks.
So you know that before you actually do the neural network for sure. You have to know that before you do the neural network.
Okay.
Yeah.
That's great. Okay, I didn't think about other possibilities because I only look at the simple example here. Okay, let's go to the next slide. Okay, so this is the features. This parser include like it has something similar. You'll see it employs the arc standard system for transition, but the input has like more information than the simple transition-based parser we talked about. So in the simple model we talked about, you remember, like the stack and buffer had only words in it as features, right? However, this model, the neural network model, its configuration has not only words, it has also there's part of speech tags, POS tags, and dependency arcs, which is written as S label here. This means dependency arcs. So the official explanations are like listed here. The S word is vector representations for some words, some of the words in the sentence S, and their dependence at the top of the stack sigma and the buffer beta. We get to choose the S words here, and correspondingly there will be S tags and S labels of them. So the S tag, the POS tags, comprise a small discrete set which has like I think it means single noun. I don't know about this. This one's plural noun, and it's something else. And the arc labels also comprise a small discrete set, which is this one, adjective modifier. I know this, like non-subject noun.
So that's a dependency relationship, right?
Yes. The label is literally the dependency arcs, the dependency relations, and the tags are these things, like these POS tags for each word.
It's a rule that each single word played in the speech. Yeah.
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 Okay. So each type of these, I don't want to call them feature here, but okay, each type of the feature has the corresponding embedding matrix. So an embedding matrix, do you remember that? It's a linear mapping from the original space to a higher dimensional space. So here it's like all list of words and their corresponding embeddings. So it's like embedding matrix of the words, embedding matrix of the POS text, and embedding matrix of the dependency arcs. Okay, so sorry about the noise. So now let's talk about the example here. Here's a sentence: he has good control, and it's from this paper, Chen and Manning, in 2014. They selected 18 words as the S word. What are the 18 words? They are the top 3 words on the stack, the top 3 words on the buffer, which is 6 words, and the first and second leftmost children of the top of the 2 words. It's a bit confusing here. So I equals 1 means S1 is for the top word, and S2 means the second top word. So the first and second leftmost dependent, the children just means dependent. Dependent of the top word, which is 2, plus the first and second rightmost dependent of the top plus 2, and then first and second rightmost dependent of rightmost of the, oh.
Or you would need to hand over to me. I can explain this part using the slides right here.
Oh, okay. Now let me hand over this to Daniel to help me to count them.
Yeah, it's a bit complicated right here for this page. I'm going to share my screen here.
Oh, let me exit my share first.
Yeah. So basically, this is the same kind of example Jing just mentioned, previously. So we have a sentence. The sentence is, he has good control. He has good control. Okay. So the stack has 3 different words right here: root, has, and good. So that's our already that's kind of like initial words that we already have. So this is 3 kind of words here. We could have another 3 words like a control, or over something, right? There's another 3 word in buffer, or even more words over there. So those are just our kind of initial input over here, stack and buffer. Okay, so that's word 1, word 2, and buffer word 1. So how do we actually define which word is word 1 and word 2? Is like we start from the right, not left. Okay, so this is a stack. We actually start from the top of the stack. Okay, we do not. This is not like a first in, first out. It's like a last in, first out. Okay, so we actually start from the top of the stack right here. So this good right here is the first kind of word, and S2 here has is the second word, and that's the third last one here. But we don't actually count it a word because it's a fake kind of rule we just created. So the first kind of word in the buffer is control. Okay, so like Jing said, we have 3 classes of different features for each kind of like a input right here. So for the first word, the word itself is good. The part of the speech is GG. I don't even know what that means, but I think it's a adjective, like descriptive or some kind of like words like that. And dependency relationship, no, because we don't actually create any dependency relationship yet. So we don't have any dependency relationship. So this is empty. Okay. So similarly, S2 has is a verb and no relationship. Control in the buffer is is a nominal or noun here and doesn't have any relationship yet. So this is not the everything. This is not the entire kind of initial or the input we're going to use. We still have a little bit more to do. For example, the second layer could be the left arc of S1 here. Okay, left arc of S1. That is the left arc of good here. So as you can see, left arc of good is the empty, the part of speech is the empty, dependency is empty. But why is that like empty? That's a question actually I want to ask for you guys. Try to think about it yourself. Like when we do the left arc, just think about the left arc action we did previously with Jing. Why when we do the left arc of good, we don't actually get anything? Someone just answer the question. That's control in the buffer. What's the left of good? Control is not the left side. Control is like the right side, actually. If you recall, like I ate fish, right? The left arc of it is I, not fish. So it's not about control.
There's nothing on the left of has.
So on the left is has, yes. And does has and good has any relationship right here?
So first of all, S1 is good, right? S1 is not has.
Yeah, so you can go from has to control, then control to good, right? But there's no direct dependency relationship between has and good, right?
Yes.
Right? So in that case, that means we don't have any words to the left. And what's part of a speech? Because we don't have a word, so we don't have part of speech, let alone of a dependency relationship, right? So now using the same kind of logic, what about the right arc of S1, right arc of good? Why is it all empty again? Any thoughts on this?
Because there's nothing. No one is dependent of good.
No, it has something over there. If you do the right arc, you can shift the words, remember? You can shift the control. You can shift the control to the stack.
Yeah, but it should be like a red, it should be like a left arc from control, right?
I think Jing just mentioned that. Good is a children of control.
Yeah.
But is control something of good? Which one is the head? Which one is not the head?
Control is the head.
Yes, control is the head, good is not head. So can we actually go from good to control?
No.
No, but we can do another way, right?
Yeah.
So that's why it's empty. Because you cannot go from opposite direction. It has to go from one direction to another direction. It has to go from the head to the, which is control, to the good, but you cannot go back. Remember, it cannot be a loop. Does that make sense? Because if you go actually from good to control, then when you loop to the word of control, then you have a control to good. Then it's close like a loop. So it actually, you know, kind of like a distorted the tree structure. It's not a tree anymore. Does that make sense to you guys?
I'm thinking from another point.
Yeah, go ahead, go ahead.
Because like, I think we need to consider the time step at this state, right? Like we're looking at this one and seems like we can guess what's the last like action that like the neural network predict. It could be shift. So that's why we have like good in the stack. So at this time, this is the current state. And at this state, we don't have like arc relationship for good because it just came to the stack. And at this moment, we want to make the prediction of what should happen next. So I'm just thinking maybe maybe those like arcs hasn't been added yet, because like for a machine, it doesn't know like which one is the right direction, right? Because that's what it's trying to learn. So that's kind of like how I read this.
But here, it seems like, you know, but here the thing is like everything here is the input. We don't actually do any prediction. So all
Right,
those.
but like say for this, like at this step, you make a prediction from the actions and you take that action, right? And then you have a like updated state.
No, Lilian, we don't actually make any prediction for the input right here. So it's just like it's already over there. So if you go to the paper right here, or actually just go to this, let's go to the notes right here. So as you can see here, those are just input right here. So we use
I understand their input, but these input like it doesn't look like that. Like at the very beginning, the stack only has a root, right? And something happened to make it like shift over and like become the state.
Oh, I see what you mean. Okay, so you said this is a middle step. This is not like the initial, like the first step over there. Oh, I see. Okay.
They wrote it down there. Note that we use a special null token for non-exist element. So when the stack does not have anything yet, like it's empty, it still has the position which is occupied by the null. So I think that makes it like not only the middle step, but like always like a frame of how to do it.
Yeah, I think like no matter it's a middle stack or not, like even you add control over there, it doesn't actually, it doesn't actually come with a dependency relationship because it can be, because you cannot go from good to control over there, right?
But I mean, like the purpose of this neural network is to fail and learn, right? So it doesn't know which can go, which cannot.
I see what you mean. Yeah, that may be another explanation over there. Yeah.
Well, it's just, I haven't read the paper yet, just my hunch. So I'll read the paper and I'll let you know.
Yeah, sure. Yeah, because I read the paper. It seems like they are taking this as the input over there. But yeah, it could be like it's a middle step. It's not like an initial step over there. But yeah, let's talk about this later. Anyway. So yeah, very good point. Thanks. So for word 2 here, which has, if you do a lateral arc, apparently you has he right here, right? It's not in the stack. So why do we have he here? Because we just shifted from the buffer. Okay, it has already like a shifted from the buffer, so it's not in the buffer anymore when we go to this step. So he is to the left of has. So now we have a tag for the he, and now the relationship is built. Okay, so we have he has right here. Okay, so next part is the right arc of second word. Again, if you go to the right, it has good here, but has and good doesn't have any relationship over there. So it's actually empty over there. Okay, it's actually empty over there. Okay, so basically that's how everything is organized. So the input here in each kind of like layer could be the word itself. It also could be all the arcs, because in each step we have to explore all the words inside the stack. Okay, in each step we have to explore all the words inside the stack. So we have to find, we have to actually use up all the words. We do not only use a word, but we also use the relationship between the words. So everything here is an input for the neural network. So that's why we have 1, 2, 3, 3 words right here. Left 1, 2, 3, 4, 4, 3, 4, like 7. But we also could have yeah, I guess that's, can we? Yeah, I think we also can have like another kind of layer, which is the left arc of left arc S1, left arc of good one. On top of that, we do another left arc. Again, we can do this for right arc as well. So that's why when you go back to the slides here, when you go back to the notes here. So suppose we have 6 words, just like what we had before. He has good control over something. Okay, so 3 words in the stack, 3 words in the buffer. So that's a 6 input already. Okay, so next we're gonna do left arc of word 1, right arc of word 1, left arc of word 2, and right arc of word 2. Okay, so in total, this could be 8 combinations, 8 different combinations over there. Okay, 8 different combinations over there, just like what we did here. Okay, what we did here. The next part is because we are only, when we do a left arc of word one here. So when we do a left arc of word one, we move to here. Okay, we move to here, but we are not at the end of the stack. We still have a root here. So we can do another one. We can actually move a little bit further to the root. That's why in the next step, we do another left arc on top of the left arc, another right arc on top of the right arc. Okay, so that we can explore all the words. And of course, the right arc of good and the right arc on top of the right arc could be nothing. But if it has nothing like inside this kind of like a dependency, you just use the now to represent it. Okay, now token here. And the corresponding post tags is, 8, because, you have like 18 here. So this is 4 plus 8 plus 6. You have 18 kind of elements in there. So you should have like 18 tags. But for the label, for the corresponding like dependency relationships, we only count that start from left arc or right arc. We don't actually count those like words right here, because the word itself doesn't correlate to each other. Like it doesn't have any dependency relationship. Starting from here, we actually count how many dependency relationships we have. So we get rid of the 6th one, 18 minus 6. So we are left with 12. Okay, we are left with 12. So after that, we just concatenated all this kind of like, features, and we actually use a dense feature like representations. I think we'll get a touch on this in assignment 3. I think like a producer from the embedding matrix, like because we use embedding for each word, then we transform that into a dense feature representation. Then we concate all the words or flatten them into one single vector. Then we put that as the input for next step. Yeah. So basically that's my part for the explanation here. Any questions so far about this one?
Okay. Someone asked why he is not treated as an input. He is treated as a token. Like for the words, we throw 18 words in it. If it has some words like he, blah blah blah.
I think this part corresponds to Le Yuan just said. Maybe we're just in the middle. We haven't put he inside the stack yet.
Wait, I thought he is a part of the input. I don't know.
Well, it's just a general case. I think if he is here in a certain step, it doesn't matter, because this node just tells you like it has 6 words and their children, their grandchildren in it. And if there's no such dependent or no such word, it's replaced by null. It's still a token there. It doesn't affect the counting.
What do you think, Le Yuan? Do you think it's in the stack, like for this step right here, like a he?
Yeah, I think the second from the last row, the LCS2.
Yeah.
I think this is just like what happened before, right? We have already added this arc. It has been added to the relationship set.
Yeah.
So it is treated as a part of the input.
Before that, I don't think he was inside the stack, right? Or it could. Yeah. I don't think it's like before that he was in the stack. I think it's like when we do the left arc of the second word, then we add he into the stack.
Yeah. I'm just looking at the paper, and it's not the first step. So the first step is he is like they move the he in the stack into stack, and right. It's actually 1, 2, 3, 4, the 5, the 5th row after the. Like the 4 actions.
Oh, after the RCS1, then you add into the stack. Yes. Yeah, I think, that's my understanding.
Yeah, he's right.
Yeah. So at the beginning, he's not an input. Actually, only when you do the left arc or right arc, you just shift the words from the buffer to stack. Then it becomes an input. Yeah.
And I think I would like to add like my understanding of this neural parser.
Yeah, sure. Go back to the slide. I'm going to stop my
share. Okay, it's not technical at all, just like my small summary. I didn't write it here. Okay, so that was my question. My question was why are there so many features? Why don't we just use words, right, like before? So these features, we know it seems to be way more complex than we learned 10 minutes ago. It's because the neural network will tell us which action to choose in the next step, given the current status, right? It's not like we choosing the next action. So we just throw in a lot of features and get the neural network to tell us what to do. And these features, they change the long and sparse 0101s, like one-hot encodings of the words and other things into dense and feature representations. That's why these features are like so complex. Yeah. And here I listed 3 papers for further reading. The first one is just the paper of the neural parser we just talked about. And the third one is a MALT parser, which is a widely used conventional parser. And the middle one was listed in the official notes. So if you're interested in more details, please visit these brilliant papers. And I hope we can talk later about any questions. Okay, is there any question here? Okay, so that's it. Or is there Daniel or Jiachen, do you want to add anything as comments?
I think we can go to, like, I have some notes on the evaluation part.
Sure. Let me
So
stop
we
sharing.
can go to evaluation like a little bit, then down for the day. So just give me 1 minute to.
Okay.
So just give me 1 minute. I'm just gonna connect to the Zoom here. Any question here about previous notes or any question about previous lecture we just went through? It's 4, 3, 2, 5. Gotcha. All right, I'm gonna share my screen here. So this is gonna be a last part of today's lecture and evaluation. Yes, so we talked about all these kind of different models, right? But at the end, we have to evaluate the models. Like, how do we know we did a good job, or we actually, like, a model sucks at actually, parsing all those kind of different components in the sentences. So there are 2 ways of evaluating the dependency parsing. So the first way is called UAS. So it's called unlabeled attachment score. So I'm going to just highlight this. Unlabeled attachment score, also called UAS. So basically just look at the correctness of the signed head, ignoring the dependency relationship. So it basically just look at whether the 2 like different kind of words are linked together in the right way or not. Okay, so it corresponds to the number of corrected predicted dependencies over the number of possibilities, ignore the dependency relationship. So for example, suppose we have this sentence, she saw the video lecture, okay? And we have, this is the gold standard. This is like a Treebank or the test or the final standard we're gonna look up to. This is our model. That's our model. So what we're gonna do is like, we're gonna see whether all those kind of like, nodes or the words are linked to the right nodes or not. So if you look at this one, 4552, 4552, 202012. Perfect. But except for this one. So in that way, we're going to count how many, incorrectly predicted combinations we have, and divide it by that, and we just get rid of that, and we count how many correctly predicted combination we have. Then we use the correct number to divide by the entire number, which is 4 by 5, 80%. And that's why we have 80% here. Okay, so we don't care about the tag. We don't care about the label here. We don't care about the relationship. Okay, so that is, we don't look at this. We just look at, this part. Yeah. So that's UAS. And second kind of evaluation is called LAS, Labeled Attachment Score. So this is pretty much like a UAS, but on top of that, we do not only care about the correctness of a signed head, but we also care about the correct dependence relation. Okay, that is, we do not only look at this, but we also look at, whether the tags, part of speech tags or the dependence relationship are, right or not, especially this part, actually mainly just this part. Okay, so if you look at those two tables, that's the right one, that's the wrong one. We already have the wrong kind of connection, so that's counted as 1. And for this one, it's nominal, noun or phrase, and this is a different one, nominal subjective, objective, that's comp. So these two are different. It doesn't actually match the right one. So we have 1 plus 2, 3 incorrectly predicted records here. And what about the left two? The left two are the right one. Okay, so we use the right number, which is 2 divided by 5, then we have 40%. We have the 40%. Okay, so actually, I was talking with Jia Chen earlier this morning, because this lecture doesn't require us to remember all those kind of labels here. So I'm kind of curious, how often do we are actually going to use this? Or most of the time we're going to use that. So I don't know yet, because I just get started assignment 3, so I don't know how we want to evaluate that part. But for now, I just want to introduce both definition to you guys so that you know how to evaluate the parser or the dependency parsing models here. Okay, any question about this part? If you don't have any question, then we are done for today, because we are out of time for today. So probably I'll just leave an assignment to next week to go over. And yeah, you still have 1 week to do assignment, so make sure you actually do it yourself. And if you have any question, feel free to DM me or just send over some kind of WeChat conversations with me. So any question about anything else? All right, thank you. Oh, I think someone. Okay, I saw Lilian has a question. So thank you to Jia Chen, thank you to Jiang Jing. They actually prepared a lot of really fantastic details on all the kind of lectures. I was totally impressed by their kind of the way they talk, and also the way they actually establish all those kind of logics when doing all these kind of lectures. And I hope you guys like it, and hope you guys can at least learn some stuff from this. And thank you so much. Thank you, everyone. And hope you guys have a really wonderful Sunday, and see you guys next week. Okay. So, all right. I'm going to leave the meeting, and bye-bye.